You are holding a teaspoon. The ordinary kind, silver or stainless steel. The kind you use every morning to stir coffee or add sugar to tea. It feels light in your hand. You could hold 100 of them and feel almost nothing. A teaspoon weighs about 5 grams. 5 grams is the weight of a few grains of rice. A feather. Nothing. Now imagine filling that same teaspoon with something else. Not water, not sand, not lead. Something that exists in the most violent places in the universe, where the laws of physics stop playing by the rules we thought we understood. Something so dense that a teaspoon of it would weigh as much as 1 billion tons. Not 1 billion tons. 1 billion tons. To feel what that means, you need a comparison. The heaviest object humans have ever built is the International Space Station. All of it. Every module, every panel, every piece of equipment floating above your head right now. The station weighs about 420 tons. A commercial airplane, like a Boeing 747, weighs around 412 tons. So, the entire space station, the most massive structure humanity has ever assembled in orbit, weighs almost exactly as much as one jumbo jet. Now multiply that. Not by 10, not by 100. Multiply the entire International Space Station by 2.5 million. Stack them, crush them, compress them all down into something you could fit inside a teaspoon. That is what we are talking about. A single teaspoon. This is not theoretical. This is not speculation. This is real material that actually exists. Right now. In places we can observe. In places we are actively studying with the most powerful telescopes on Earth and in space. You have probably heard the term before. Neutron star. It sounds scientific, clinical. Something to nod at during a documentary and forget about 5 minutes later. But when you actually understand what a neutron star is, when you grasp the physical reality of what it means to compress 1 billion tons into 5 grams, something shifts in how you see the universe. Because neutron stars are not distant abstractions. They are the ruins of dead stars. Massive suns, far bigger than our own, that lived for millions of years before dying in the most catastrophic explosion physics allows. When a star with enough mass reaches the end of its life, it collapses inward with such violence that electrons are crushed into protons. The space between atoms disappears. Particles are forced to touch each other. What emerges is something that should not exist according to our everyday intuition, yet the universe creates it routinely, casually, as if it were the most natural thing in the world. The surface of a neutron star is smooth. Not smooth like glass. Smooth like geometry itself has been compressed into it. A mountain on the surface of a neutron star would be measured in centimeters, not kilometers. Centimeters. If you could stand on one, and you could not, because the gravity would kill you instantly, but if you could, and you dropped something from waist height, it would hit the ground at something close to the speed of light. Except you would never hit the ground. Before you fell any distance, you would already be stretched into atoms. Your molecules would be pulled apart like taffy. This is called spaghettification, and it is what the tidal forces of a neutron star would do to any object unlucky enough to get close. But it starts long before you reach the surface. It starts miles away. The gravity is so strong that it does not pull evenly. Your feet would be pulled harder than your head. You would be torn apart from the inside out while you watched it happen, unable to stop it. This is the universe showing us something we never wanted to know about the nature of space and gravity. And it is real. We can see these objects. We can detect them. We can measure their properties and understand them with the physics we have developed. They are not mythology. They are not fiction. They are the aftermath of stars we have observed. Stars that we watched explode. So why are we starting with a teaspoon? Because a teaspoon is small. A teaspoon is something you understand. You have held one. You know exactly how it feels in your hand. And when you take that familiar object and tell someone that filling it with neutron star material would require a force equivalent to the weight of 2.5 million international space stations, something in the human brain recognizes that this is not normal. This is not something that fits into our world. This is a message from the deep universe, written in physics, telling us that we do not understand the extremes that nature can reach. And that is where we start to grasp what a neutron star really is. Let us go back to the sun. You have seen it. You see it almost every day. A yellow-white disk in the sky that is bright enough that you cannot look at it directly without burning your eyes. It feels close. It feels personal. It is 93 million miles away, and it is so far that light from its surface takes 8 minutes and 20 seconds to reach you. 8 minutes. That is the distance the sun is from Earth. That is how far away you are, right now, from the fusion reaction that keeps you alive. The sun is massive. It contains 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, all of it combined is less than 1% of the sun's weight. The sun is so heavy that it bends space around it. Gravity is not a force pulling you down. Gravity is curved space. The sun is so massive that it curves space like a bowling ball, resting on a stretched rubber sheet. And you roll toward it because the sheet is tilted. The sun weighs 2 septillion tons. That is a 2, followed by 24 zeros. Try to visualize that. You cannot. Your brain cannot hold a number that large. So, we compress it. We compare it. You could fit 1.3 million Earths inside the sun. Imagine taking our planet, the entire Earth, with all its mountains and oceans and canyons and the weight of the whole thing, and fitting 1.3 million of them inside the sun. That is just the size comparison. That is not even getting into the weight. Now hold that number. The sun. One star. One massive, gravitational monster that could swallow our world more than 1 million times over. A neutron star is formed when a star much bigger than our sun dies. When we say much bigger, we mean something that started with at least 20 to 30 times the mass of our sun. Imagine a star that was 30 suns, crushed together into a single sphere, fusing hydrogen into helium for millions of years. That is the kind of star that creates a neutron star. And when that star runs out of fuel, something extraordinary happens. The sun will not do this. Our sun is too small. In about 5 billion years, the sun will swell up into something called a red giant, and it will probably engulf Mercury and Venus, and possibly the Earth. It will be dramatic and terrible for anything alive in the solar system, but it will not create a neutron star. Our sun will just die, slowly, and leave behind a white dwarf, a dense, stellar corpse, but nothing like what we are about to describe. A star 30 times bigger than the sun? That star will end differently. When the fuel runs out, there is nothing left to hold up the weight of the star against its own gravity. The star has been fighting gravity its entire life, using the outward pressure of nuclear fusion to balance the inward crush of its own weight. But when the fusion stops, the game is over. The star falls inward. Not slowly, not gradually. It collapses in seconds. The entire star, this massive object made of gas and plasma, and all the heavy elements forged in its core, falls inward at a speed that eventually approaches the speed of light. The density increases. The temperature increases. The pressure increases. And then something fundamental happens. The star is so compressed that electrons are forced into protons. Electrons and protons merge. They become neutrons. And suddenly, you have a star made almost entirely of neutrons. No empty space between atoms. No atoms at all, really. Just one vast quantum object made of degenerate neutron matter, held together by the strongest force known to physics. This object is typically only about 20 kilometers across. 20 kilometers. The city you live in is probably bigger than that. And inside that 20-kilometer sphere is the mass of our entire sun, plus the mass of several suns. Compressed. Absolute. Real. A teaspoon of this material would weigh 1 billion tons. Let that land. 1 billion tons in 5 grams. That is 200 million tons per gram. That is 40 million tons per milligram. If you could hold it, and you could not, because your hand would be vaporized instantly by the energy radiating from it, but if you somehow could, you would be holding enough weight to crush the planet beneath you. But we can go deeper into the physics. Neutron stars spin. When a massive star collapses, it is like a spinning ice skater pulling in their arms. The star was rotating slowly before the collapse. But when it compresses down to the size of a city, the rotation speeds up. A star that was rotating once every few days suddenly rotates once every second. Some neutron stars rotate 30 times per second. Some rotate more than 1,000 times per second. 1 rotation per millisecond. That is faster than any human being could perceive as motion. The surface of such a neutron star is moving at a significant fraction of the speed of light. At the equator of a rapidly rotating neutron star, the surface is moving so fast that if it rotated any faster, it would tear itself apart. Physics itself would not allow it to spin more quickly. Imagine a city-sized object made of the material that can fit 1 billion tons into a teaspoon, spinning up to the speed of light. And as it spins, it sends out beams of radiation, electromagnetic waves, light, high-energy particles, sweeping across space like a cosmic lighthouse. These beams are called pulsars. They are so regular, so perfectly timed, that when astronomers first discovered them, they thought they might be signals from alien civilizations. The pulses were too regular to be natural. They seemed like a message, but they were not a message. They were just a neutron star, spinning, sending out its beam, every rotation like clockwork. Some pulsars pulse so regularly that they are more accurate than atomic clocks. For a few decades, we had better timekeeping data from a dying neutron star than we had from any instrument we had built ourselves. The radiation from a pulsar comes from the motion of charged particles in the intense magnetic field of the neutron star. And that magnetic field is not normal. The magnetic field of a neutron star is so strong that it would rip the iron out of your blood from miles away. The magnetic field is about 1 trillion times stronger than Earth's magnetic field. At the surface of some neutron stars, the magnetic field is even stronger. These objects, called magnetars, have magnetic fields that would be lethal at a distance of 1,000 kilometers. If you got close enough to see it with your eyes, the magnetic field would already have killed you. And yet here is something that should gut punch you. We are not even at the extreme yet, because there is something inside the neutron star that we can barely understand. At the center, the density becomes so extreme that the physics we use to predict the behavior of normal matter starts to fail. At the core of a neutron star, neutrons might be crushed so tightly that they break apart. Quarks might be forced to touch each other. The matter might transform into something called quark matter. We do not know for certain. We have never actually observed the interior of a neutron star. We cannot. No light escapes from the region where it is being formed. But theoretically, at the center of a neutron star, matter might reach a state of density that is still not completely understood by modern physics. This is what separates the neutron star from everything else in the universe. It is not just dense. It is not just heavy. It is a place where the universe is doing something that our best physics still has trouble explaining. It is a laboratory for understanding matter at extremes that we can never recreate on Earth. When we study neutron stars, we are studying the universe's way of showing us the limits of what we thought we knew. And they are everywhere. Not everywhere in the literal sense, but distributed throughout the galaxy. Hundreds of millions of them, probably billions. The remains of stars that died billions of years ago. Some are isolated. Some are in binary systems, where a neutron star orbits another star, slowly pulling material from its companion, growing hotter and brighter as that stolen material falls onto its surface. Some are in pulsars, sending out their beams to sweep across the darkness. Some are in X-ray binaries, systems so violent and bright that they would outshine entire galaxies if we could see them from Earth. They are not rare. They are not impossible. They are just uncommon enough that we do not have one nearby to observe up close. And that might be the only thing saving us. If you could somehow capture a teaspoon of neutron star material and bring it to Earth, what would happen? It would sink. It would not stop at the surface. It would not rest on the ground. The gravity pulling down on an object that heavy would be so intense that the material would sink through the Earth like a stone through water. It would sink through the crust, through the mantle, down toward the core. It would sink through the core, and it would keep sinking until it reached the center of the Earth, and even then, it would not stop. It would continue falling, in an endless orbit, through the planet, from one side to the other, forever. Actually, that is not quite right. Before it sank very far, the friction would kill it. The intense heat from the material around it, the pressure, the forces at work, it would all transfer energy to that tiny spoonful of neutron star material. And the neutron star material would lose its coherence. It would break apart. It would decay. But for a moment, just for a moment, there would be something inside Earth that should not exist in our world. Something belonging to a place where the laws of physics are written differently. This is not a practical thought experiment. It is not a prediction of something that could happen. It is a story we tell ourselves to understand what neutron stars are. Because understanding neutron stars is about understanding the extremes of the universe. And the extremes of the universe are about understanding what we are, where we are, and what the universe is capable of doing. We are made of carbon and oxygen and nitrogen. The heavy elements that were forged in the cores of stars and scattered through space when those stars exploded. We are made of stardust. That is not poetry. That is literal fact. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in the core of stars that died billions of years ago. You are the universe observing itself, made from the ashes of dead suns. But you are not made of neutron star material. You are made of the remnants of ordinary stars. Stars that were not quite massive enough to become neutron stars when they died. Stars that became white dwarfs instead. Slowly cooling remnants that would take longer than the current age of the universe to cool down completely. This is not an accident. This is not chance. This is the way the universe works. The universe creates neutron stars routinely, through stellar death and explosion. It creates them and leaves them scattered throughout the galaxy. But the universe does not concentrate them, does not bring them into contact with each other in ways that would spread neutron star material around. They are isolated, mostly alone, spinning their beams across the darkness. Except sometimes they are not alone. Sometimes two neutron stars collide. When two neutron stars merge, the gravitational wave that is released is so powerful that it can be detected across billions of light years of space. In 2017, scientists detected such a collision using the LIGO gravitational wave detector. Two neutron stars, moving at nearly the speed of light, had spiraled into each other after millions of years of slowly losing energy through gravitational radiation. They had been orbiting each other, getting closer and closer, until finally, they touched. And when they touched, space itself shook. Gravitational waves rippled outward through the universe at the speed of light. And when those two neutron stars merged, they created something new. The collision was so violent that it triggered a thermonuclear explosion. Neutron star material was thrown into space at enormous velocities. And in those moments, at those densities, at those temperatures, something remarkable happened. Elements heavier than iron were created. Gold, platinum, uranium. The heavy precious metals that we value, that we use in our jewelry and our technology, that we build our most precious objects, from much of it was created in collisions like this. Much of it came from the collision of two neutron stars. This means that somewhere in the jewelry you wear, somewhere in the precious metals of your heirloom or your ring, there is gold that was created in the collision of two neutron stars. You are wearing a piece of the most violent event in the modern universe. You are carrying with you the remnants of a catastrophe that was so powerful that it sent gravitational waves rippling across 1 billion light-years of space. This is what the universe is. Not the comfortable parts. Not the parts with stable stars and habitable planets, and life learning to question itself. Those are special. Those are precious. But they are not all of what the universe is. The universe is also neutron stars. It is also collisions of incomprehensible violence. It is also matter so dense that a teaspoon would weigh 1 billion tons. It is also radiation so intense that it would kill you from miles away. It is also gravity so strong that space itself bends around it. We live in that universe. Not because we are brave or special, just because we happen to form here, on this planet, around this star, in this galaxy. We happen to form in one of the rare places where the conditions are right for life. But we could have formed anywhere. We are made of the same material as the neutron stars. We are made of the same particles that they are made of, just arranged differently. The difference is arrangement. The difference is time. The difference is luck. A massive star is born from a cloud of gas and dust. It burns for millions of years, fusing hydrogen into heavier elements. It grows massive and hot and bright. It lives for ages, and then one day, it explodes. The explosion scatters its material across light years of space. Some of that material falls into a new cloud of gas. That cloud collapses. A new star is born. And if conditions are right, planets form around that new star. And if conditions are even more right, life emerges on one of those planets. This is what happened to create you. And the path that led here went through the death of stars. It went through the violence of supernovae. It went through the collision of stellar remnants. It went through the creation of gold and silver and iron and carbon. All of the complexity of your body, all of the thoughts in your mind, all of your consciousness and awareness. It is the product of stellar violence. You are made of dead stars, not metaphorically, not poetically, although it is poetic. You are literally made of the material that was forged in stellar furnaces and scattered into space by stellar explosions. And some of that material was created in collisions between neutron stars. Some of what you are came from the most extreme violence the universe can produce. But you did not turn into a neutron star. You became, instead, a person. You became aware. You became conscious. You became able to think about the universe that made you. You became able to understand, through mathematics and observation and thought, the nature of the cosmos. You became able to know that you are made of the ashes of dead stars, that you are the universe becoming aware of itself, and the neutron stars are still out there, spinning, sending their beams across the darkness, waiting, colliding, creating new elements, dying, in their way. Even though they are already dead, the universe does not stop. The universe does not rest. And we, who are made of its material, who are part of its ongoing transformation, we do not rest either. We look at the darkness. We ask questions. We try to understand. A teaspoon of neutron star material would weigh 1 billion tons. That is not a reason to be afraid. It is a reason to be aware. A reason to understand that we live in a universe that is capable of extremes beyond our intuition. A universe that is vast and violent and beautiful. A universe that made us. A universe that we are part of, forever, no matter how much lighter and smaller we are than the objects that created us. You are made of the material of dead stars, and that material is still moving.